Okay, so it should start recording. Let us start. So yeah, so we completed the discussion on detection, and mainly we spend a lot of time on RCNN architectures. We will also sort of end this topic with an extension, with a very nice extension of faster RCNN also, but that is more like an application to segmentation. So let us go into segmentation. So segmentation we have sort of defined very loosely earlier when we defined the tasks, that is detection, segmentation, then instance segmentation, and so on, right? So semantic segmentation is semantic segmentation is the task where you basically give a finer boundary. So in detection, what you give is sort of these bounding boxes, which are a tight bounding box, but still it does not say, I mean, it can include a lot more other, I would say, objects or backgrounds inside the box. But yeah, it tries to make sure that the whole object is inside, whole object that is visible in the image that comes inside the box. But these extra parts are always there. So segmentation actually overcomes this limitation, and it tries to put a finer boundary, more fine-grained boundary, you can say, across the whole object. So this was a cat in the original image, so it will try to put it like this. Now it is not only just the object, it can yeah, I mean, in semantic segmentation, it tries to give labels, sort of. Okay, don't think about labels at this moment, but it tries to give the fine boundary or finer boundary to all the, so that it covers all the pixels. So this is one, which is tree. That yellow one is cat, the green is grass, and the blue is sky. So one way to do it is that is, I mean, one way you can think what semantic segmentation or how semantic segmentation can be handled is basically thinking of it as these pixels and giving labels to it. So if you think these pixels, these nearby pixels, and if you can just classify them as the class belonging to sky, so there are maybe these 4 classes in this data set. So you are trying to basically classify these pixels, all the pixels in the image, to belong to one of the 4 classes. So these will belong to sky, say this will belong to sky, this will belong to sky, but this one should belong to tree, or maybe this belongs to grass, but this belongs to basically, or this should belong to the cat. So in a way, you can think it as a dense prediction, what is called dense prediction task. So you need to predict densely. That is, for each pixel, you need to put out a classification decision. So sometimes it is also called a pixel-wise classification. So initially or earlier, what you did for image classification, you classified the whole image as one class, right? But for this, I mean, for even the detection, what did you do is you classified the whole sort of region proposal. Okay, here you need to classify each pixel, right? So we will come back to that when we will go into some methodologies for semantic segmentation. Another one is instance segmentation. Another type of segmentation is instance segmentation, and there is a very, very subtle difference between semantic segmentation and instance segmentation. The word instance is of course important. It basically needs to give different instance, different identity. So suppose here, so these 2 are dogs. So in the original figure, these 2 are dogs. So if you go via the semantic segmentation definition, then all pixels belonging to dog will be categorized as dog. So these pixel, this pixel, this pixel, this pixel, all pixels will be classified as dog. But instance segmentation demands demands that you also basically demarcate between different instances. So, or the pixels belonging to different instances should also be classified as a different instance of that object. So this is dog 1, this is dog 2, something like that. Okay, and this is cat. So we will see how we will do. I mean, we will just discuss very briefly about one representative method on instance segmentation, and that is the that will be the concluding thing in our discussion about applications of deep learning, convnets rather, and that is the mask RCNN. That will be the extension of faster RCNN. So let us go ahead. Again, if you have any questions, please stop me by raising your hand. Okay, anytime. Now, this is a very naive idea, semantic segmentation sliding window. So we first, when we started discussing about, okay, I see one question coming. So can you, yeah, I'm let me. Yeah, Ritovan, you have some question?
Yes, sir. In the previous one, you said that instance segmentation differentiate between the instances. So that means if the same image was passed to semantic segmentation, would the two dogs have the same, like be colored with the same color, so to say?
Exactly. It will not tell that it is dog 1, dog 2 or something. Okay, two differences. Okay. Exactly. What you thought is right. Yeah. Okay, yeah, you can lower your hand. Okay, let me go to this. Yeah, so the naive idea, probably naivest idea, not naivest, I mean, there are other unsupervised clustering based methods are there, but maybe naive idea employing deep learning. So sliding window. So when we started discussing about detection, we also thought of this, right? That, okay, we will just do different sliding window. Sliding window basically here means that, okay, different crops. So different dense crops, and then you classify whether it contains a cat, dog, etc. Here also you will do that. Very similar approach, but you will take very small crops. So like this, or maybe let me take a different color. Maybe this is a better color. So like these or these smaller ones, and you basically base it on each pixel. So the center pixel of these crops you basically take, and then take a small sized crop, say maybe 10 by 10 or something, 5 by 5, whatever. And that is your this crop, say the first crop, and you pass it through the classifier. This is just simple AlexNet classifier. This was used in this paper in PAMI 2013. And you classify, I mean, whatever your classifier gives, you assign that level to this center pixel. So at least this center pixel is classified. Now you go to the next center pixel. This is this blue bound or blue crop. For that, it is also giving cow. So it is coming from, say, this region, right? It is giving that, okay, this crop belongs to cow. So you will tell that, okay, this center pixel belongs to cow, and so on. This is grass, and so on. So that's a very naive idea. You can always do it, but problem is very inefficient, not reusing shared features between overlapping patches. So it is not even using the shared features, because convnets, if you pass this whole image, I mean, the features coming from this crop and features coming from this crop, they have something in common. Even if you don't pass, I mean, even if you don't think that, okay, you are passing it through convnet, just if you think that, okay, this is the image, and these are the overlapping patches, the red and blue, you are still sort of recomputing it for these individual crops. You are not passing it through, I mean, you are not reusing the sharedness or sort of shared areas of the crops. So very inefficient. I mean, you need to pass a lot of crops and so on. So this is not a good idea, but this is of course a good start. Okay, and that is way back in 2013 and 2014. These sort of ideas were used. So what can be another idea? Another idea is basically fully convolutional. So fully convolutional. Why this makes sense? So for that, let us try to understand what is the input and what is the output. So the input is, of course, 3 cross H cross W. So 3 basically means the number of channels. So sometimes you will see number of channels appearing at the end. Sometimes you will see that number of channels appearing at the very beginning, right? So this is the RGB channel. This is H and W, that is height and width. Okay, so now suppose you have 20 classes in this data set, or 20 different objects, and all the rest. So 20 different objects, maybe cow, grass, tree, sky, etc. And everything else is sort of a background. So you basically, I mean, it is very similar to the detection philosophy also. So everything else is a background class. So in that sense, you will have, say, 21 class classification problem, right? So what did I say? That each pixel needs to be classified as one of these 21 classes. So your output will be, for each pixel, a 21 length vector, right? 21 numbers will be there, whose sum will be 1 and each will be a positive number, right? So if that is the case for this pixel, this pixel, this pixel, everything, for every pixel you will have this 21 numbers. So what it means is that you will have 21 channels. So HW, still the same H and same W, but here you had 3 channels, here you will have 21 channels, or number of classes, right? So what is your input and what is your output? Your input is still H cross W, output is also H cross W in spatial dimension. What is changing is the number of channels. So here it was 3, here it was C, right? So if you just try to process the image without using any pooling operation, so what does or what reduces the size of the image in the feature maps? The pooling operations, because you can think that you are using the half padding convolution with stride 1, okay, or some other stride you can use, but accordingly your padding needs to be modified. But you can keep the size same by using conv, okay, only conv, but pooling generally doesn't allow it, right? So that is the whole idea. Why was pooling needed? I mean, that we discussed way back in when we discussed the elements of coordinates, right? Those equivariance, so slight shift invariance, translation equivariance, or also to reduce the computation. So many reasons, among the many reasons, those two are important. One is the translation invariance, and basically the reducing the computation. Because if you need to say operate a 3 cross 3 on this H cross W, that is say the I'm taking the VGG ballpark value, so 224 by 224 image size. So you need to basically and your output is also 224 by 224, so you need to place or perform this 3 cross 3 convolution 224 square times, right? Every pixel location in the output, right? So I think that should be clear from the convolution arithmetic that we discussed probably a month ago. So a lot of computation happens at every layer. But if using pooling, you are say making it half to 112 by 112, at least in the second layer, you will have to compute 112 square into say 3 square into number of input channel and number of output channel, right? So this is reduced from 224 square to 112 square, right? That is the advantage of pooling. But what we are saying is that we will not use pooling, because pooling, if you use pooling, then you will not get this H cross W. So the advantage is that, okay, you are getting the semantic segmentation. So after you get this C cross H cross W, that is 21 cross H cross W, at each pixel you get the argmax. So whatever is the maximum maximizing class, you give that level to it. So that way you are getting an output, right? So I should not have drawn it here. Maybe it was there, but just to show you, make you understand, I drew the channel here. But this is actually the output. The output is ultimately H cross W cross 1, you can say, because that is the argmax value. But for visualization purpose, it is also 3, because you need to color code in basically RGB. So, but that is a different thing. I mean, output is H cross W, you can think. Okay. So the summary is that you can sort of get rid of pooling, or sort of not use pooling to get this size, same spatial size segmentation map, but that means it will introduce a lot of computation, right? So the advantage that you get by employing pooling of reduction of computation, that you don't get. Okay. So this is the disadvantage. So what do you do? That is the idea. Or if we can do this thing that, okay, this is sort of normal convolution. So you basically do this the 3 cross H cross W, then after basically pulling pulling once, it becomes H by 2 by W by 2. Then again you pull, it becomes H by 4 by W by 4, and so on, right? So these things, and then if you can actually sort of reverse the process after that. So you have H by 4 by W by 4. From there, say you get H by 2 by W by 2, and then H by W. Then only you can, it will serve your purpose. So from 3 cross H cross W, you get a H cross W image or segmentation map, right? So we need to do some sort of an upsampling. So what is an upsampling? That will come. So downsampling was that pulling operation. So that reduces the size. So it should increase the size. The upsampling should increase the size. So downsampling we call pulling or strided convolution. What or how can we get upsampling? So let us see some. Start with some easy methods, and then we will go into one of the sophisticated ones. So one idea is in-network upsampling, or sometimes it is called unpulling. So these are some terms that they, the first users of these things coined. So what is unpulling? One very simple is that you just duplicate. So you have this input 2 cross 2, you want to get an input of 4 cross 4. So you just duplicate this 1, 1, 1, 1, this 2, 2, 2, 2, 2, 2, and so on. Whatever the value is, you just duplicate. But it gives generally some artifacts, and there is no learnability. So we'll come to how can you basically use sort of a convolution idea, very similar idea like convolution in unpulling also. But let's wait for 1 or 2 slides. Another very simple is bed of nails, which is just you fix one position. Okay, so from 2 cross 2 you need to go to 4 cross 4. So you divide each of these 4 cross 4, not each of these, this 4 cross 4 area into say 2 cross 2 patch. So each 2 cross 2 patch will have 4 pixels. You take the left top, and there you will put the original value here. Okay, so basically this goes here, this goes in the left top of the next position, this goes here, and so on, right? So, and the rest you fill up with 0. So that is another way people have tried this. It did work, it did some reasonable work, performance, but later we will see more sophisticated ones, right? So this is one is the nearest neighbor, another is bed of nails. Another is a small sort of hacky way of unpulling. So this has relationship to the pulling operation that has happened earlier. So let's see what this means. So you suppose you did a pulling here at this when you after 2 conv operations you did a pulling here. Okay, then again after 3 conv you did a pulling here. So what you will do is you will sort of you can think of a mirror here, and you will try to basically get a mirror image of it. So what is a mirror image? Not literally, just say it's sort of a functional diagram you can think. So you will have a convolution here because you had a convolution here, so you will have a convolution here. But now you had a pulling, so you will have an unpulling here. So it is sort of from there to there an unpulling, or increase of the resolution. Then again 3 conv, so 1, 2, 3 conv. Then you had here pulling operation, so you will have another unpulling here. So it has to maintain the relationship of this whatever max pulling did in the in its mirror component. Okay, mirror image component. Okay, why people? This is again. All these seems a little arbitrary, but it worked. And then again, from the in the next slide you will see some learnable ways too. So corresponding pairs of downsampling and upsampling layers. Now, this was the input to the actual, normal pooling or max pooling. That was the output because it was max pooled. So in this 2 cross 2 region, that 5 was the highest value. So you took 5. This 6 was the highest value in this 2 cross 2 region. So you took 6 and so on, right? That is normal max pooling, 2 cross 2 max pooling. So the input was 4 cross 4, output is 2 cross 2. Now, what does this max unpooling, the corresponding layer does is it remembers where the maximum occurred. So here in this 2 cross 2, the first 2 cross 2 patch, the maximum occurred at the top right, bottom right. So you put your 1 there. So you see the color coding, this was blue and this is blue. So you put it here. Similarly, here in the next 2 cross 2 patch, the maximum occurred at top left. So you put these 2 in the top left. So it is mostly likely most to the bed of nails. But in bed of nails, you are fixing a position. Okay, I always will put them to top left or some position that you were thinking. So here it is determined by the position that was pulled from in the corresponding pooling layer, max pooling layer. So that is sort of a hacky way, but yeah, people got success with that. So these are some non-learnable. I mean, you don't have to learn anything. I mean, in pooling anyway, you don't learn anything. There was no learnable parameter there. So, but in unpooling, you can have. So let's see. So this is learnable upsampling that we will go ahead. Again, if you have any questions, please stop me. I'm going a little fast because we lost some time. So I'm just trying to make it up. Transpose convolution, it is called also sometimes, or strided, fractionally strided convolution also it is called. So yeah, probably I am forgetting. Anyway, but at least these two are called it. Unpooling or upsampling or transpose convolution, they are used interchangeably. Okay, now, but recall the normal pooling, so normal convolution. So normal 3 cross 3 convolution, stride 1, pad 1. So you dot product between filters and output. So this is input is also 4 cross 4 and output is 4 cross 4. So because it is stride 1 and pad 1. Okay. Now, so how do this basically take place? So this is the first position of the 3 cross 3 conv layer. So basically something like this. And you multiply with these, these 9 values element wise, and you put this value here, right? So this was the padding, right? I mean, this part, this part, this part, this part, and this part was the padding. Okay, what happens to the next position when you stride it? So this is, it goes to here, this blue position. So now again, you basically multiply those 9 elements, this element wise, and you basically, element wise means the elements of this filter and the input values, right? And you put it here. Element wise multiply, sum, and put it here. So that is the sort of the normal convolution that we have seen earlier. Okay, so what is okay, so yeah, so that was the output because okay, let me see. Oh, sorry, yeah. So this is the stride 2. So if you do stride 2, what happens? You can think, you can just go ahead and do this. So this is the first position, you get this. Now you will have stride 2. So you will not start here, rather you will start from here and here. So that's what I think next slide says, because stride 2. So this is 2, right? 2 pixels. And you are getting this number. So you can't go further. So you are getting only 2 numbers. Then again, you are going via stride 2. Then that is, this 1, 2, 3, right? And so on, right? So this, and then this, you cannot go further. So this and this, okay. So from 4 cross 4, you are getting 2 cross 2 output. This is normal convolution, strided convolution. I'm just going a little fast. Okay. Now the interesting stuff. This is learnable upsampling transpose convolution. So 3 cross 3 transpose convolution, stride 1, pad 0. What does it mean? So first of all, we want to go from an input 2 cross 2 to output 4 cross 4. So that you should keep in mind, because that was the idea of upsampling, right? So we needed to do upsampling because we cannot sort of convolve on the original resolution, it will increase for semantic segmentation because it will increase the computation a lot, and it will not have that translation invariance also. So our goal is to get from a 2x2 input to a 4x4 output, right? So now how can you do with a 3x3 filter? So earlier we have seen those bed of nails, etc. Now, how can you do it? Let us go ahead. But this is the main philosophy. Input gives weight for the filter. So just I mean, I'm giving 5 seconds for you to digest. Input gives the weights to the filter. I mean, weights are generally associated with the filters, right? But the input actually weighs the filter weights, you can say. Okay, so let us see what do we mean by this. So we said 3x3 transpose convolution. So 3x3 is let me. Okay. I'm drawing this 3x3 here. Just a bigger one I need. So this is the 3x3 con filter. The values are W1, W2, W3, W4, W5, W6, 7, 8, 9. Okay. Now, when you place this filter, I mean, don't try to think placing this filter. Input gives weight for the filter. So you multiply this x1 with every value of this, right? That is what is given here. X1 into W1, X1 into W2, X1 into W3, and so on, right? That values you put here. So you are not sort of clubbing them and summing them. You are just weighing these weights, again, weighing these weight W's by this X, and you are putting these 9 values here. Okay. Now, what happens if you do the stride 1? Okay. If you stride next, you actually go one place to the right hand side of it, and then again you do the same multiplication. So X2 W1. I mean, this is okay. So this was again W1, W2, etc. Right? So now you multiply it with X2. So these are these values. So X2 is this, and so on. So you get 9 values, but you put it not on this, I mean, on top of this red sort of area. You put it on top of the, basically overlap with this blue top left, these values. Okay. So I hope you are getting what I'm trying to tell, that, okay, you get, when you multiply X1 with these W's, you get 9 values. Where do we put the 9 values? First, you put in this put by placing this top left corner with I mean, somewhere. I mean, this is the first position, so somewhere. Now you move this by 1 unit, 1 pixel here. So you have to move this top left by 1. That is sort of the idea. So if you try to do the convolution arithmetic here, it will come. I'm not going into that much detail. Just I'm trying to show you how you can basically visualize it, or sort of get the intuitive idea how it happens. Okay. So now you will have these overlaps. So these previously in the previous slide you had this okay, this one. Now you have this one in the same position. So you basically somewhere output overlaps. I mean, you can also do averaging. Even you can do max pooling there. That is, you take the maximum of these 2, 3, whatever values are overlapping. Okay. I mean, here it will be, you can see that it will be 3 overlaps, right? Because the next time it will come here, and so on. But people have found that, okay, summing actually gives basically better results empirically. Okay. So this is how you get from 2x2 to 4x4. You see, I mean, you cannot go more towards the right because X2 is exhausted. Now you have to go to X3 and so on, right? Okay. This is okay. So now that we have the components sort of learned about the components in brief. Let me actually go through these 2-3 slides real quick, so it will conclude the segmentation, I mean semantic segmentation part. Now you will understand things better of this architecture. So this was one of the seminal papers in fully convolutional networks for semantic segmentation, again from the same group, Berkeley group, Trevor Darrell's group, who were the pioneers in the RCNN architectures also. So John Long, Essence Silhamid, and I think Trevor Darrell there. And it actually got, I think, a best paper award, probably joint best paper award in CVPR 2015. Anyway, but I think this is the idea that, okay, you have the input, you normally do, I mean, first part is you do normal con, then again con, but upsampling, that is this learnable upsampling, again con, learnable upsampling, and so on. So it has the architecture, different architecture, I mean, how many layers, etc., that you can have a look at the paper. There are other hairy details. I mean, they use skip connections also, so that I'm not again giving more detail, but you can have a look. I mean, now, I mean, it should help you to understand the paper better. So this was one. Then some contemporary works using other variations of unpooling came, or upsampling came. So this was that unpooling. I think it was that. What was that? I mean, where you need to remember the max pooling, the corresponding max pool positions. Okay, so this was simply this part, left part was VGG, and it was the mirror image of the VGG. So this is called con-decon network, I think. And then they tried with some other hacky way of deconvolution, something called deconvolution also is there. I'm not going into detail of it. You will find it sort of in the paper. This is the paper. This was con-decon, and then the final contemporary one, I would say, there are lots of others, but yeah, I mean, I have just picked these three. This is the segnet, and it also used that similar type of unpooling. Okay, again, I have hurriedly gone through this, but I can stop for some questions. This is a good time to ask before I go to instance segmentation. If you have any questions on the unpooling part. Yeah. Devjyoti Dasgupta, yeah. Ask away. Devjyoti, I've asked you to unmute.
Am I audible?
Yeah.
So in the transpose convolution, there was the point that input gives weight for the filter. So I didn't get the point, since the weight of the filter still will be learned using backpropagation, right? During like,
yes.
how is input given?
Yes. I missed that. Actually, this is just to sort of, I mean, don't take it too literally. I am just telling it so that you understand this. Okay, it's so much lagging. Okay, now it has come. So that you understand it, what visually is happening. But you are right. I missed that part, that actually the learnable part are these W's, not the X's, because X is input. Filter is actually this. I mean, in the previous slide it was there. Yeah, I mean, these W1, W2, W3, this. So of course these W's are learned. Okay. So it's not that X's are learned. So though I am saying that input gives weight, basically it is, so you take it as the weighted combination. So if you take it as weighted combination, they are what weight means, that I mean. Okay, does it answer your question?
Yes.
Yeah, I see Rishabh is also, Rishabh has some question. Yeah, Rishabh, please ask him.
Hello, sir.
Yeah.
So like in practical scenario, do we use both segmentation object and what was second thing? Segmentation and that. Yes, sir. So do we use both the things simultaneously to identify, because there are loopholes in both the things? Am I right? Because segmentation gives the tight region, while the bounding boxes just gives that this is the object.
Yes. So there are basically application scenarios. Of course, people will, I mean, if they want to sort of get where the object resides, it will be better to know the finer boundaries. I mean, if you just think about this autonomous driving scenario, I mean, you are trying to basically move away from a pedestrian. So why, I mean, if you know the finer boundaries, then you can basically plan better, right? I mean, you don't have to say move to the pavement in that way. So I know, I mean, this is not a good example, but of course, I mean, having better localization is better in many other applications, maybe military applications, where precisely you need to know the positions. Okay. 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 So yeah. So let me go ahead now with the instance segmentation. Okay, so instance segmentation, I am not again defining. I think somebody asked the question, someone asked the question whether if you have many instances, all of them will be labeled as the same thing. So that is also seen here. So one thing is that instance segmentation not only wants to detect the individual object instances, but also wants to have a segmentation mask of each instance. So what can be a naive idea? How can you do this thing? I mean, just have a look at this. Not only wants to detect, but wants to have a segmentation mask of each instance. So I am just allowing you to unmute. If you can, you give me a naive idea, how do you do it? Anybody, any idea?
First,
We can
perform
color
object
the entire
detection.
bounding.
Sorry, yeah, one by one. Yeah, please.
So we can color the entire bounding box with the different colors.
So first you need to have the bounding box, right?
Yes, sir.
Ritavan, you were saying something?
Yes, I was saying that first perform object detection and then do segmentation in each.
Yes, exactly. So that is the naive idea, and that is what we will discuss. So both are right, Devjyoti and I think Ritavan. You need to have the bounding box sort of, and then you will do the segmentation. So instead of the sort of doing it on the detection bounding box, you are doing it on the region proposals. So that's sort of the idea that we will see in the next, I mean, in the next philosophy. Okay. Let us go ahead. So that is the basic idea. So mask RCNN. So we have seen now the fourth variant of RCNN. So RCNN, sometimes people call it slow RCNN, though it is RCNN, and then faster, and then now mask. So mask RCNN is nothing but faster RCNN with FCN on ROIs. What is FCN? Fully convolutional network. Okay, so fully convolutional network is this. I probably missed it why we are calling it fully convolutional, because there is no FC layer connected here. Okay, so you are basically doing this classification. Ultimately, you might think that, okay, ultimately I have to output 21 numbers or C numbers for 1 pixel, but you can do it via 1x1 convolution with 21 or C plus 1 channels, output channels. Okay, so it does not include any fully connected layer, so it is called convolution, fully convolutional, though actually it uses pooling and unpooling, but basically fully convolutional means no fully connected layer. Okay, so that is the basic idea. So you have this image, then you have these ROIs, just like the faster RCNN. Then previously you were doing ROI pool, but here you need to do ROI align, because ROI pulling it and then trying to do a segmentation in that ROI does not give you the intended result. It does not sort of close the gap between the within the cup and the lip, right? So it's not just getting that final mile. I mean, that's what the issue was. So ROI pool uses some approximation that will come, but ROI align basically better deals with this approximation, and that we will see. Okay, but after that you get this proposal, and then I mean the similar thing. I mean the classification head and this segmentation head. Even you can have the detection head also. So this is sort of the full idea. I mean a brief idea, but we will go into the details next. I mean, this is again, instance segmentation methods, but yeah, I'll not go into that. The better interesting part is this. Before I go there, I see some question coming from Rishabh. Yeah, Rishabh, I have asked you to unmute.
Yes, sir. I just had a basic doubt. And in the case of instance segmentation, how will the model learn that this part of the picture exactly constitutes the boundary of a person? Maybe the person is wearing a cap and somewhere is not wearing a cap. So, I mean, how will I?
See, those sort of, I would say, occlusions that is always there, but you need to just try to improve. I mean, if the training, I mean, the easy answer would be if the training examples involves a lot of capped person and also a lot of uncapped person, then for both the scenarios, it will just classify it as person. Okay. So it all depends on the data. So if your data is good, your results will be good. Okay.
Okay, okay, sir.
Okay, let me, so you can, yeah. So let me, yeah, okay. So let me go ahead with this idea. So this is actually taken from the paper itself, the mask RCNN paper. And I just like this sort of paper. I mean, this sort of writing. I mean, if you see this sort of writing, I mean, you will probably be more interested in reading the full paper. So let me just read it for you. So mask RCNN is conceptually simple. So it is just telling that, okay, you don't need to be freaked away. It's very simple. What is that? It is faster RCNN has two outputs for each candidate object. We know that, a class level and a bounding box object or bounding box regression, we told. To this, we add a third branch that outputs the object mask. So just like I think Ritovan and Debojyoti told that, okay, you can just have the ROIs and then you have the classification score, the bounding box regression, and you can have the mask, right, on the ROI. So they are adding this third branch. Mask RCNN is thus natural and intuitive idea. Okay, but the additional mask output is distinct from the class and box outputs, requiring extraction of much finer spatial layout of the object. Next, we introduce the key element of mask RCNN, including pixel to pixel alignment, which they are calling as ROI alignment, region of interest alignment, not region of interest pooling, which is the main missing piece of faster RCNN. So introducing that actually gave this sort of finer basically bounded. So you could have thought that, okay, I have ROI, I can just do fully convolutional network sort of idea basically in your ROI. So basically what I mean is that if you just in place of this full image, you just put pass those ROIs. Okay, they have this experiment done in this paper. So that will not give as good a result as or as finer boundary as using the mask RCNN original idea, that is the ROI align. Okay. I hope you got it, that I mean, you can just pass these ROIs, candidate proposals, through the basically your fully convolutional network, right? Okay, now this is sort of some brief idea about how it happens, but yeah, I will go into more visualization later. I mean, how it happens visually. I think the next slide, but let's go ahead. So mask RCNN adopts the same two-stage procedure with identical first stage, that is RPN, that is region proposal network. So what is the two-stage procedure? It basically says that you have proposal generation and then proposal classification in RCNN. So it has the same two-stage, that is proposal generation, then not only proposal classification, but you are also using segmentation also. So identical first stage, but the second stage has some addition, right? What is the first stage? That is the proposal generation, and that is being generated by RPN, the region proposal network that we discussed last, right? Last means last week, the last class. Anyway, so in second stage, in addition to class prediction and bounding box regression that was there in faster RCNN, mask RCNN in parallel outputs a binary mask for each ROI. So this is important, binary mask, right? So you get the classification score, right, for that ROI. So if I say go to this figure, you get for say this ROI, you get the classification score that okay, it contains a percent. Now you do the bounding box offset also regression. Then you basically do a binary classification of all the pixels that belongs to this ROI. Okay, and why binary? Because you have already, you know that the your classification had told that it is percent. So you need to just classify inside this box what are percents, what pixels are percents, and what are non-percents. Okay. Again, just take it with a bit of salt, I would say, because the next line sort of contradicts it, and it will not be immediately clear, but it will be clear when we go to the visualization. Okay, the results. So the mask branch has km square dimensional output for each ROI. See, it is for each ROI. So binary mask of m cross m resolution, one for each k classes. Okay, what did I say? That okay, if it is percent, then you just have a one binary mask, right? But because your classification head gave that okay, most probability is a percent, that is the maximum probability belongs to the percent class for the ROI. But here I am saying that for each of the k classes you actually output the same percent resolution. So does it not contradict? It actually contradicts, and what I said was not actually right, and this is the right thing. And why? Now you may ask, like, why do you need to do this? I mean, you know that this is a person here. So why do you need to put a binary sort of mask, which sort of classifies that, okay, whether it say involves a cat or non-cat? Okay. Why it will be useful, we will come later when we see the visualization. Okay, now ROI pool breaks the pixel to pixel translation equivalence, and that's why they needed ROI align. So what does that mean? Let us see. Okay, so what is ROI pool breaking pixel to pixel translation equivalence? So here, let me first describe these images first. I mean, sort of input output first, at least the input. So here the input is actually 6x6 feature map. So if you think like this, if you go here, whatever, okay. Okay, so this one from here to here, I am taking. Okay, so one ROI I am taking. So this is that. And it has 6x6 pixels. So it has, in the feature map, it has 6x6 size. So 1, 2, 3, 4, 5, 6. Not these. Okay. This is a little shift from the conventional that I have shown. Okay. So these intersections are the pixels. Okay. Or rather the feature values. Now, sorry. Yeah, that was the original ROI. And okay, no, sorry, this was the this was the input feature map. Sorry, again, that was the input feature map, and these are the pixels, basically input feature map, the whole feature map, not the ROI. The ROI is this. Okay, so now the ROI, I mean ROI region is this. Here no concept of pixels, so don't think, I mean I had a also tough time to understand this. I mean I sort of had watched the actual, I think 45 minutes sort of tutorial by Kai-Ming Ha, the first author of this paper. I mean, he's also the first author of the ResNet paper. Okay, so one of the famous. I think in Google Scholar probably he's in top 10 of the citations list. Yeah, just see. Anyway, in CS. Okay. Now, so this basically is the ROI. So this is the region. Okay, so this is the region which you need to say divide it into 2x2. So these are the 4 patches, and whatever pixels basically are within this, you need to take the max, right? You need to take the max of this. So this max will go as 1, this max will go as 1 value, this max will go as 1 value, and this max will go as 1 value. And that way you will get a 2x2 basically ROI pooled sort of output that will go to the classification, bounding box regression, etc. Those heads. This 2 cross 2 just draw parallel to your what I told about 7 cross 7. So earlier using VGG, we were ROI pulling to 7 cross 7 area. So here, I mean, just so that all these fits, and I have basically enough space to basically show. I am just showing it as 2 cross 2. Okay. Now, what do you do? So if you basically project your ROI, it is getting this. Okay. But this is sort of in between 2 pixels. So how do you basically come away with it? This is sort of the implementation details in faster RCNN, but that actually caused a lot of issue in the mask RCNN. So what do? You have to basically break the tie sort of. I mean, if I may use the word tie, but what it tells is that, okay, this corner is between 2 pixels. So I shall move to the nearest one. So the nearest, I mean, there are 4 sort of neighbors, 1, 2, 3, and 4 for this pixel. So I'm basically moving it to here. So I'm just changing a little bit the size of the bounding box so that this moves here. Similarly, this has the nearest neighbor here. So you are putting it here. So this you are putting here, this you are putting here, and similarly. So you have to either stretch it a little bit and those on. Now you see where things are going wrong, because your projected ROI was giving you this. If you could have used these original ROI, you could have probably got a more finer, more subtle boundary, but you have to basically, you are bound to do this stretching, expanding, and so on. Otherwise, how can you basically get this max pooled values, right? Now, after you get this position, you basically divide it into 4 regions. I think that this was the region, whatever, and you max pool it from there, right? So this was a bad thing. ROI pool coordinate quantization. So you need you are introducing some quantization error. Okay. Now, what do these ROI align do? I mean, I'll try to basically explain it to you, but I'll also encourage you to look into that 45-minute talk or something. I think in ICCB 17 itself there was a tutorial. Anyway, so ROI align, what does it do? So it would have been good if you can basically use these areas. Maybe this is the region. So remember that these are pixels, but these are not pixels. This is not pixel, this is not pixel. These are just areas, right? I mean, this is just a bounding box. So if we could have pixel value here, that would have been good. But what they are doing is also very clever. So just forget everything. Just focus on these orange bounding box. What you need to do is you need to divide this bounding box into 2 cross 2 patch. So what are these patches? So this, and similarly the other. I'm not, not cluttering it. That's why I'm just removing this. So in this patch, I mean, if it was an ideal sort of scenario, in this patch, you would have gotten a lot of pixels. And from there, suppose this one was a pixel, this one was a pixel, this one was a pixel, and this one was a pixel. So you basically take the maximum value of it, and that you will put here. You take the pixel maximum value of the pixel to these 2 pixels here, because there are only 2 pixels inside, and you put the maximum of it. But you see the problem in this design. Here there are like 4 pixels here, 2. So how can you make it more regular? Because that may not give good results. Okay, so how do you do it? Again, I am trying to declutter it a little bit. What they do is they put regularly placed sort of virtual pixels. So this is one virtual pixel, this is another, this is another, this is another. So in each such region, each such patch, okay, you put 4 virtual pixels. So you now have 4 pixels in each patch. And if you can get values for these 4 pixels, then you can just max pool out of these 4 pixels for each patch. Okay, so you don't have to max pool from 4 pixels somewhere, 3 pixels somewhere, 2 pixels somewhere. No, you have 4 virtual pixels in each of these patches, and you are basically max pulling it from there, right? So how do you get these pixel values? That is interpolation. So interpolation is basically, I mean, since this is a 2D one, so you get you do 2D interpolation, or sometimes it is called bilinear interpolation, right? So if LINEAR, if you want to know more to bilinear interpolation, just go to Wikipedia. That is basically, I mean, it's sort of an extension of just interpolation. So in interpolation, you have this value, you just use unitary rule and put this value. In binary, you basically just take four nearest neighbors. So here, the 4 nearest neighbors are these, and these, the 4 nearest pixels. You just do this binary interpolation. Similarly, for this, I think the same nearest neighbors are there. For these, I think these, and these, and so on. So you get all these 4 virtual pixel values. Now you max pull. You max pull, you put it here. You max pull from these 4, you put it here, and so on. So this gave better, finer boundaries. I'll stop a little bit here. I'll just have to show the visualization, and I just have to explain that K cross M, sort of K M square binary, or K M cross M binary mask thing. That is only the thing that is left. But if you have any questions on this ROI align, ROI pooling, please ask us. This is a good time to ask. It's a little surprising that everything got into you, because yeah, it's a sort of a little difficult concept to grasp. But yeah, I mean, it's not. I mean, it's intuitive. So yeah, maybe you can sit down sometime and have a look and try to understand more. And there are resources. I mean, this paper, this paper and this tutorial that is there. Okay. So let me quickly go ahead with these visualizations only. So I mean, this is incredible. I mean, these are not ground truths. These are really the predictions. So, and it gives good basically, let me use a different color. It gives very good, I mean, the confidence also. Person with confidence 100% confidence. Subboard with 1, and so on. So here person is 0.9. Now, this is, you see, disconnected object. Now think about this bounding box. Okay, so this was the ROI. This already your classifier has identified this as the person. Now, if you do binary classification on this, yeah, I mean, if you do the binary segmentation mask prediction, that is for all pixels in this ROI, you want to classify it as person or non-person. Rather, it is a better idea to go ahead with this bounding box, this surfboard. Okay, surfboard is the blue color, right? So if you want to basically do this binary classification mask prediction, that okay, which pixels are surfboard, which pixels are not. So basically it will say that okay, either it will say that this is surfboard and this is, I mean, this part, this is surfboard, or this is not, right? So if it tells it is surfboard, then you are getting this as I mean, whole thing as surfboard. And I think if you go here for the person, you will try to classify the same pixels with whether it is person or non-person. Now you need to decide which one to put, right? So what you do is for everything, I mean, you see the disconnect, right? I mean that, okay, which one will you take? Which binary mask will you take? So what you do is you basically try to predict all the binary masks for all the classes in all ROIs. And whatever, I mean, if person gave better probability, or these pixels being person gave better probability, higher probability than these same pixels being say surfboard coming from these ROI, then you put it as person. So it helps a little bit on this sort of disconnected objects or occluded objects, right? So this is, I think at least I could think of this as the advantage. I mean, it was never clearly mentioned why they have this K times, I mean, K binary mask predictions, but I could think this. Okay, so that is one thing. These are again some very incredible results. So this is from another data set that was, I think, from Coco, the other one, previous one. I think, let me see. Yeah, it was Coco. This is from Cityscapes. So that's an autonomous driving sort of like, I mean, it's a driving scenario data set. Now you have some failure cases also. So that is the last slide. The failure case is recognition. So, I mean, in case of recognition, I mean, this is the thing is masked very good, but it gave it as a kite. So, I mean, but this seems to be reasonable anyway. So, okay, so this concludes this sort of detection segmentation application discussion, and we will start with actually the recurrent networks tomorrow. Okay, any questions on this part or anything? Okay, okay, if you don't have any questions, then okay, we will meet at I think 12 tomorrow, and actually